No one alive today will leave the solar system, and it's quite possible that no human being in any future generation ever will. It's not for lack of will, nor lack of money, nor lack of courage. There is an invisible barrier made of pure physics that traps any carbon-based animal like you within this small cosmic neighborhood. And the strangest thing is that this barrier probably also traps any other form of intelligent life that exists out there. There could be millions of civilizations spread throughout the galaxy, and it's very likely that none of them will ever truly be able to venture into deep space. A lot of science fiction, and a lot of science communication as well, treats the exploration of the galaxy almost as an obligatory step, a matter of time, something that every advanced civilization ends up solving sooner or later. But there's a serious problem hidden in that assumption. The barrier that blocks this expansion is made of just two things: dust and emptiness. And each of them, in its own way, is almost impossible to overcome. You don't understand the size of space. No one truly understands. The human brain evolved to deal with distances like next door and on the other side of that hill. It wasn't built to distinguish between very far and a million times very far. Both sentences produce the same vague feeling in your head, even though they're completely different categories of things. The Milky Way alone has between 200 and 400 billion stars, and the Milky Way is just one among at least 2 trillion galaxies that current telescopes can detect. Against that backdrop, the entire solar system, sun, Earth, all the planets, all the moons, occupies such a tiny fraction of space that it practically doesn't exist on any scale worth drawing on a map. And even this tiny point, your own cosmic backyard, is already too big for any spacecraft that humanity knows how to build today. There's a quote from the physicist Richard Feynman that helps us understand why it's still worth trying anyway. In a 1965 book called The Character of Physical Law, he described how it's a great adventure to contemplate the universe beyond humanity. He described imagining what it was like before there was any eye to see it. That's basically the purpose of this video, to use speed, not imagination, to try to feel the real size of what's out there. The fastest human being who ever existed was an astronaut returning from the moon in 1969. At 40,000 kilometers per hour. Fast by the standards of anything that moves on wheels, but pathetic by the standards of space. The fastest object ever built by humans to date is the Parker Solar Probe. It uses a kind of gravitational trick, skimming past Venus repeatedly, stealing a bit of the planet's orbital energy with each pass, until it gets trapped in an increasingly tighter orbit around the sun. On December 24, 2024, after 6 years of doing this, the probe broke the record, reaching 692,000 kilometers per hour. Fast enough to go all the way around planet Earth in just over 3.5 minutes, or cover the distance to the moon in 33 minutes. The probe is named after the physicist Eugene Parker, who theoretically predicted the existence of the solar wind in 1958. Decades before any instrument was able to confirm that it existed. Parker watched the launch of the probe bearing his own name in 2018 at 90 years old. To survive at that speed so close to the sun, the probe carries a carbon shield just over 11 centimeters thick, which can be pointed directly at the light. On the exposed side, the temperature rises to about 1,370 degrees Celsius. On the other side of the same plate, in the shade, the instruments operate close to room temperature. The entire difference between surviving and melting, in this case, comes down to an 11-centimeter thick plate. There's a simple mental exercise to grasp the size of the problem. Imagine a manned spacecraft capable of that record speed, ready to go explore the solar system. A regular rocket today takes 7 to 10 months to reach Mars, at a distance that ranges from 55 to 400 million kilometers, depending on where the two planets are in their own orbits. This hypothetical spacecraft would make the same journey in 2 weeks. Not bad. The next destination would be Pluto, almost 6 billion kilometers from the Sun, reached after about a year. Much farther, but still within reason. From there, another 2 years to cross the heliopause, about 18 billion kilometers away, the boundary where the solar wind stops pushing back interstellar space. And another year to surpass the distance that the Voyager 2 probe launched in 1977. Took almost 50 actual years to travel. The next destination is the outer edge of the Oort cloud, the true boundary of the solar system, where anything that still orbits the sun ends and real open space begins. This edge is about 1.5 light years away, something close to 15 trillion kilometers. In this hypothetical spacecraft, traveling at the record speed of any object humanity has ever built, the journey there would take 2,500 years. That's not just a long time. It's the amount of time that separates the founding of the Roman Republic from the moment you're processing this sentence right now. And after crossing all that time, there's absolutely nothing waiting on the other side. Just emptiness. That's the invisible barrier. The barrier isn't made of stone, it's made of nothing. There's always a very distant place that, with human ingenuity and billions of dollars, can be reached. That was true of the summit of Everest, the bottom of the ocean, and the moon itself. The problem is what happens when you pull the camera back one more time, and then again, and realize that you've barely even started to really move away. So why not go faster then? No one knows a real, non-magical way to travel faster than light, teleport entire bodies, or freeze crews for decades. A warp drive isn't just a science fiction writer's invention. There's even a serious proposal for it in the physics literature. Mexican physicist Miguel Alcubierre published in 1994 a valid mathematical solution within general relativity, which describes a bubble of space contracting in front of the ship and expanding behind it, allowing in theory faster than light travel without directly violating the local laws of physics. The inconvenient detail is that this solution requires an enormous amount of negative energy, a type of matter that no one has ever observed to exist in any useful quantity. In practice, it remains elegant mathematics with no engine behind it. Propulsion systems based on nuclear fusion or antimatter, on the other hand, strong enough to reach a relevant fraction of the speed of light, are within what physics allows, at least in theory. It's worth imagining what that speed would feel like from the inside. No sensation of continuous acceleration. After the initial boost, the ship would float in almost absolute silence, with no gravity, no engine noise crossing the void, at a speed so far beyond any everyday reference that, looking out the window, practically nothing would change from one day to the next. That's the kind of contradiction that the cosmic scale imposes. The most extreme speed that physics allows felt as almost complete immobility. Here I need to be honest with you. All this optimism about reaching 20% of the speed of light bothers me a little. Not because the physics is wrong, it's not, but because real engineering today barely gets close to 1,000th of that speed. The most serious study ever done on the subject is from 1960. A project called Daedalus, conducted by a volunteer team from the British Interplanetary Society, led by engineer Alan Bond. The goal was to design, using serious physics and no magic at all, an unmanned probe capable of reaching another star within a human lifetime. The result, published in 1978, was a spacecraft weighing 54,000 tons, of which 50,000 tons were just fusion fuel, capable of reaching, at most, 12% of the speed of light. Not even the 20% that this video is optimistically assuming. Fusion engines in practice are still, to this day, just laboratory projects that have never actually flown. That said, ignoring for a moment the technical details and all the real problems that these energy sources still have, can we optimistically assume that one day it will be possible to build a ship capable of flying at about 20% of the speed of light? That's already an astonishing speed. 60,000 kilometers per second or 216 million kilometers per hour. Fast enough to reach Alpha Centauri, the star system closest to ours, in 20 years. At that speed, interestingly, time hardly distorts at all. Relativity predicts that at 20% of the speed of light, a crew would age only about 5 months less than those who stayed on Earth over the course of an entire 20-year journey. That's far too little for any science fiction plot about astronauts returning young to an unrecognizable world. The time distortion in this case is real but subtle. The problem was never that time passed differently. It was always the distance. The real project pursues this exact goal of 20% of the speed of light. It's called Starshot, announced in 2016 with funding from billionaire Yuri Milner and public support from physicist Stephen Hawking. Probes the size of a postage stamp attached to a reflective sail, accelerated by a battery of lasers with 100 gigawatts of power, firing for about 3 minutes, aimed at Alpha Centauri. On paper, it works. There's just a small problem. Internet. Nanoride. No, just kidding. The real problem is much more serious than Wi-Fi. Space, in a very literal way, is hostile to anything that tries to cross it too fast. Unfortunately, there are some obstacles in the way. Literally, because although space is very empty, it's not completely empty. There are energetic particles, gas, dust, and things bigger than dust floating around out there. As anyone who's ever crashed a car knows, going too fast and bumping into something is always a serious problem. And at 20% of the speed of light, that's still true even when the thing you bump into is just an atom. A single iron atom colliding with your ship's hull at that speed carries enough energy to carve a groove of destruction a few tenths of a millimeter deep. Over time, the hull would become riddled with microscopic holes, which isn't exactly good news. Engineers have already thought about this and created a type of shield, a kind of protective sail that absorbs or at least slows down most of the molecules that hit it. This makes the journey much safer. The problem is that there are things floating in space that are bigger than atoms. Colliding with a single grain of dust at 20% of the speed of light is like hitting a grenade head-on. A small detonation, the grain explosively evaporating, gradually corroding the protective shield. And you could collide with something even bigger than a grain of dust, a small rock, the size of a golf ball. Hitting that rock at that speed releases more than twice the energy of the nuclear bomb dropped on Hiroshima. Things bigger than that aren't even worth mentioning. Atoms, dust, and pebbles are already dangerous enough. The reason why all of this goes so wrong so quickly is simple. In a way that, in my view, Feynman himself liked to explain physics. Kinetic energy increases with the square of the velocity, not in direct proportion to it. Doubling a car's speed doubles the stopping distance you might expect, but actually it quadruples the energy involved in a collision. At 20% of the speed of light, that square stops being just a textbook curiosity and becomes the reason why a grain of sand behaves like a cannonball. That might actually be the natural speed limit. Besides the fact that no one really has a clear idea of how to fly any faster than that, all the destructive effects of colliding with whatever is floating in the void get much worse as the speed increases. T-Thiem Wang and Abraham Loeb, two of the physicists behind the calculations used by the Starshot project itself, published a study in 2017 in the Astrophysical Journal that quantifies exactly this scenario. A probe traveling at 20% of the speed of light toward Alpha Centauri would take 20 years. Their conclusion was that interstellar dust, not the distance, is the most critical obstacle of the entire project. That's why any real mission would probably need to send dozens of probes at once to ensure that at least one survives intact to the destination. The same study calculated that even interstellar gas doesn't come for free. Heavy atoms colliding with the surface of the probe throughout the entire journey would carve grooves about 1/10 of a millimeter deep into materials like quartz. It's not much by itself. Multiplied by 20 years of uninterrupted travel, it becomes significant. That's why engineers involved in the project started studying materials like graphene and beryllium copper alloys to coat these probes, trying to find something thin enough not to add much weight and strong enough to survive the very act of moving too fast. All that being said, it's reasonable to assume that, with enough shielding, a spacecraft could survive a journey at 20% of the speed of light, long enough to reach at least the nearest stars within a reasonable time frame. There's just one more problem to solve. Almost everything that's close in cosmic terms is disappointing. The first real target outside the solar system is the Alpha Centauri system. That means about 10,000 years with a slow, realistic spacecraft, or just 20 years with this fast, hypothetical one. There is a way to imagine this journey. A small group of people locked in a cramped box for 20 years, hoping to survive each other until the end of the journey. There is already a real clue as to how this would work. Between 2010 and 2011, 6 volunteers spent 520 full days locked inside a module in Moscow, in an experiment called Mars 500, faithfully simulating the isolation, communication delay, and boredom of a real trip to Mars. 520 days was already enough to alter the crew's hormones, mood, and social behavior in measurable ways. A real trip to Alpha Centauri would take at least 14 times longer than that. 4 years after their arrival, the radio message sent by this crew would reach Earth. And the content, in summary, would be something like this. The planets of Alpha Centauri are beautiful up close, but completely deadly and uninhabitable. The astrophysics you can do there is fascinating, but everyone's tired of freeze-dried food and no one is really sure anymore why they agreed to make this trip. This isn't dramatic exaggeration. Alpha Centauri is actually a triple system. 2 stars similar to the Sun, called Alpha Centauri A and B, orbit each other every 80 years, plus an isolated red dwarf, much farther from the other 2, called Proxima Centauri. Guillem Anglada Escudé and his team, in a 2016 study published in the journal Nature, confirmed a planet the size of Earth, orbiting this red dwarf, within the zone where liquid water could exist. The problem is that this planet is probably always showing the same face to its star, and it's battered by violent stellar flares, enough to strip away any atmosphere over time. The pattern repeats itself. TRAPPIST-1, a system with 7 planets almost the size of Earth, discovered in 2017, about 40 light-years away, orbits a red dwarf, so unstable that the chance of any of these atmospheres surviving the stellar flares is low. Barnard's star, just 6 light-years away, the very target chosen by that project, Daedalus, decades ago, had planets announced and then disproved by more than 1 team of astronomers. Different, which shows how hard it is even to confirm if there's anything solid orbiting these nearby stars, let alone if that thing is habitable. Even for science done entirely from a distance, without going anywhere, these closest neighbors still keep their secret. That's the problem with space. Almost all nearby destinations, if nearby still means anything at this scale, are disappointing. Not from a scientific point of view, of course. It would be an absolute privilege to set foot on another planet and admire the wonders of the universe up close. But if 20% of the speed of light is really the practical limit, and if you consider a reasonable travel time, within a human lifetime, something like 40 years, the maximum range is around 8 light-years. It took me some time to understand something about this calculation. What's frightening isn't the distance itself, it's the absence on the other side. You can emotionally accept that a place is very far away. What the brain resists swallowing is the idea that after so much effort, there's absolutely nothing waiting for you there. None of the targets remotely within that range seem worth decades of travel inside a cramped box, crossing through some of the most lethal environments imaginable. Your solar system is somewhat unlucky in that sense. You're in a relatively empty pocket of the galaxy. This pocket has a name, the local bubble, a cavity of rarefied gas about 1,000 light years in diameter, carved out by a sequence of approximately 15 supernovas that exploded nearby over the past 14 million years. The sun entered this cavity about 5 million years ago, and today it's near its center, which helps explain why the space around it is even emptier than the already empty average of the galaxy itself. This could change in a few million years as the sun moves through the Milky Way. But today, that's the situation. Supposing it's possible to go farther, to any star within the nearest stellar neighborhood, a sphere about 25 light years in diameter, in about 200ths or 0.02 of the entire Milky Way. This small bubble currently contains 34 stars and 6 brown dwarfs. Only 3 of them really resemble the Sun. One of them is the Sun itself. The other is Alpha Centauri A. The other nearby stars are mostly red dwarfs, with planets that range from deadly to extremely deadly. Sirius, the brightest star in the night sky, is in there, 8.5 light years away, far too hot and surrounded by too much radiation for anything resembling life. Wolf 359 and Leyland 21185 complete the list of the closest neighbors. Dim red dwarfs, which most people have never heard of, precisely because they shine too faintly to be seen with the naked eye. Even though they are among the closest objects that exist outside the solar system, some planets are in the habitable zones of their stars, where liquid water would theoretically be possible. But Mars is also in the Sun's habitable zone, and Mars is terrible. Even the planets that most resemble Earth among these neighbors don't come with any guarantees. An example of this kind of disappointment disguised as hope. It's Wolf 1096b, a planet almost the same size as Earth, discovered in 2023, orbiting within the habitable zone of a red dwarf about 31 light years away. On paper, it seems perfect. Similar mass, the right distance from its own star, a real chance of having an atmosphere. In practice, this planet also has the same side facing the star all the time. One side in eternal scorching daylight, the other in eternal freezing night. Exactly the kind of detail that only shows up after you take a closer look, and that no distant glow can warn you about in advance. An old silent library. Stefan Dreisler and his team, in a 2020 study published in the British journal Monthly Notices of the Royal Astronomical Society, they confirmed 3 planets orbiting a red dwarf called GJ 1061d, just 12 light years from Earth. The outermost of these planets, named GJ 1061d, receives from its own star an amount of energy similar to what Earth receives from the Sun. That's enough for it to officially make the list of Earth-like planets. Spending your whole life traveling just to end up on another Mars would be a brutal disappointment. Some stars would be genuinely interesting targets, with truly habitable planets, with oceans, breathable atmospheres, probably some form of microbial life, and who knows, maybe even more than that? It would totally be worth visiting those places. The problem is that they could be tens or even thousands of light years away. That means journeys of hundreds or thousands of years, even at a considerable fraction of the speed of light. The James Webb Space Telescope is already able to analyze the chemical composition of the atmosphere of some of these distant planets, looking for gases that would only exist there because of biological life. That's quite a game changer. For the first time in history, It's possible to study the entire atmosphere of a world from afar without going anywhere and without spending a drop of fuel. But studying isn't the same as visiting. You might end up knowing, with a lot of confidence, that there's life on some planet 200 light years away and still never have the slightest real chance of getting close to it. There is, of course, the possibility that a future humanity, much more technologically advanced and much more motivated, will find solutions that today seem impossible. Maybe that humanity will have solved biological aging, and a travel time of a few hundred years will no longer seem impossible. Maybe they will be able to send ships guided by artificial intelligence, carrying frozen embryos, or some future version of that idea. They would probably have much more advanced telescopes, capable of precisely choosing star systems that are neither deadly nor empty. This kind of proposal isn't entirely new. Back in 1964, the engineer Robert Ensman proposed a generation ship powered by nuclear fusion, a mirrored sphere over 300 meters in diameter, filled with frozen fuel, carrying several generations of crew members who would be born, live, and die on board before any of them set foot on a new world. The project never left the drawing board, but it clearly illustrates the magnitude of the mindset shift required. Not a journey, but an entire lineage dedicated to finishing what the founding generation started. I have to admit, I can't really picture that. A civilization spread out in ships separated by hundreds of light years, unable to exchange a single message in less than a matter of centuries? Would that still be a civilization in the sense that the word has today? I'm not sure it would. It's still hard to imagine, without real science fiction technology, how this kind of network could manage to stay connected or even coherent. The more you think about deep space, the less sense it makes. The distances are just too great. There's a deadly speed limit. And even if those two problems were solved, almost every remotely reachable destination might not be worth a trip. Space is the greatest challenge humanity will ever face. And today, you simply don't have the equipment or capability to solve it. Rocket, computer, even nuclear fusion reactor, all of that is still too weak for a problem of this size. A radically transformative technology is needed. Something as strange to your current standards as landing on the moon would have seemed to a hunter-gatherer 10,000 years ago. Looking up and seeing only a disk of light fixed in the sky, with no clue at all that one day someone would set foot on that ground. A real way to measure this leap already exists. The Soviet astronomer Nikolai Kardashev proposed in 1964 a scale to classify civilizations by the amount of energy they are able to control. A Type 1 civilization controls all the energy available on its own planet. A Type 2 civilization controls all the energy of its own star. Humanity, by the most optimistic estimates, hasn't even reached Type 1 yet. And even an entire Type 2 civilization capable of surrounding the whole sun with a structure to capture its energy would still run into the same problem of dust and emptiness we've discussed so far. Controlling energy is not the same as solving the problem of distance. This, by the way, helps explain something that was left open at the beginning of this video. In 1950, during lunch at the Los Alamos laboratory, the physicist Enrico Fermi interrupted a conversation about flying saucers with a question that became famous. Where is everybody? If the galaxy has between 200 and 400 billion stars and is old enough for any advanced civilization to have had time to colonize much of it, why is the sky silent? Since 1960, when the astronomer Frank Drake pointed a radio telescope at two nearby stars in search of any artificial signal, in a project called OSMA, the answer has remained the same. Nothing. Decades of listening, practically not even a whisper. Programs searching for extraterrestrial signals are still active today, scanning ever larger portions of the radio spectrum without a single confirmation. That barrier of dust and emptiness might be part of the answer. There doesn't need to be an exotic explanation, nor any sign that intelligent life is rare. Maybe it exists in abundance, spread throughout the entire galaxy, and is equally trapped, each civilization isolated in its own bubble of a few dozen light years, exactly like you are trapped in yours. Will there be a day when that changes? No one really knows. But it's worth remembering one thing. Few human activities make someone look as bad as trying to predict the future of technology. On October 9, 1903, the New York Times published an editorial called Flying Machines That Do Not Fly, predicting with complete confidence that humanity would take from 1 to 10 million years to achieve flight in heavier-than-air machines. 69 days later, the Wright brothers took off for the first time in North Carolina. 66 years after that, human beings set foot on the moon. And yet, even knowing all this, the human species has already sent a message into that void. The two Voyager probes, launched in 1977, carry a gold-plated copper disc organized by a team led by the astronomer Carl Sagan. Sounds and images from Earth, different languages, music, the heartbeat of a person in love. Voyager 1 will pass close to another star, less than 2 light-years away in 40,000 years. Sagan himself wrote at the time that launching this bottle into the cosmic ocean said something hopeful about life on this planet, even without any guarantee that someone, someday, will find it. There's a good chance this video will seem as naive as that editorial 100 years from now. And there's a whole other option, different from everything that's been said so far. Maybe this whole way of thinking is simply wrong. Maybe the future of the human species isn't really out there, spread among the stars. Back at the beginning of this video, the idea was to use speed instead of imagination to try to feel the real size of the universe. The same great adventure that Feynman described decades ago, contemplating the universe beyond humanity. The whole calculation was done, and the result wasn't exactly what science fiction usually promises. I started looking at the sky differently after working through the whole calculation carefully from beginning to end. I no longer see a map of possible destinations up there. I see pure distance stretching in all directions, completely indifferent to any plan you try to make to overcome it. Feynman himself used to say he liked living without knowing, that doubt never made him afraid, only curious. Maybe that's the only possible answer here as well. The barrier isn't made of stone, it never was. It's made of emptiness, and emptiness can't be crossed, only accepted. Maybe the future isn't out there. Maybe it's right here inside.